expect. So you just want to look at your correlation matrix to see that everything's going on as you would expect. And I think it's something that you'll get more and more intimate with your correlation matrix as you try to uncover the dimensions in your data, particularly when you really have no idea what the factor solution will be, and you're really just trying to get an idea of how you should adjust your factors. But in this case, it's pretty simple because I know there's 3 factors, and I have familiarity with the TAS-20 questionnaire. The next table is the KMO and Bartlett's test. So the KMO sampling adequacy, a lot of people, not very many people look at this in this day and age. It's quite, I wouldn't say it's very common to see it reported. People specify a rule of 0.50 and above. So this table is basically trying to tell us, is giving us information as to whether it's even justified to do a factor analysis on this correlation matrix. I think just looking at the correlation matrix, you get an idea of, yes, it merits being factor analyzed. The KMO gives a one numerical representation of how factor analyzable it is, and anything above 0.5, people's, it's a rule of thumb people use, is good. I think sometimes even as low as 0.4 can be good, can be all right, particularly when you're analyzing items and it's a really messy data set. You can still uncover something meaningful, but in this case here it's 0.88, so it's very, very appropriate to conduct a factor analysis. Then you get Bartlett's test of sphericity, which is really not reported either, and it's basically testing something that's not very interesting. And I think really you can summarize what Bartlett's test of sphericity is. It's testing that there's at least one statistically significant correlation within the correlation matrix, and I wouldn't say that's very interesting. Maybe historically it was useful because doing a factor analysis 80 years ago took something like 800 days because you had to do it by hand. So you'd probably want to do a Bartlett's test of sphericity, which was quicker, to tell you that yes, you should be doing a factor analysis, rather than doing the factor analysis and then getting to the end and going, wow, I just wasted 800 days of my life. But in today's day and age, we can just look at the correlation matrix quickly, and we can look at the significance levels. But I will note that in something called partial confirmatory factor analysis, which I'll do a video on as well, Bartlett's test of sphericity ends up being useful. So if you're ever interested in doing a partial confirmatory factor analysis, or you're interested in learning what that is, it's going to come up again. The anti-image covariance and correlation matrices, I think what's really only interesting here, in my opinion, is the measure of sampling adequacy is reported for each and every variable, and again you can use, it's on the principal diagonal of the anti-image correlation matrix, and we can see that every single one of them is above a value of 0.5 or 0.4 depending on what you use as your demarcation criterion. This can be useful when you're not sure if a variable should be included, and we can see that we're still going down here, 0.9s, 0.9s, 0.8, 0.9. They're all very good on the main diagonal. And oh, this one's not great, so that's 0.58. So things are starting to get a little bit perturbed by the time we get to item, what is that, something like 16, 17. But it's still high enough to include. But this is highlighting to me that there's going to be these items might cause some problems later on. But it can be a useful way to look at your data to help you decide which variables to exclude. So even though the correlation matrix should be factor analyzed, it doesn't mean that every single item should be included in the factor analysis, and the measure of sampling adequacy reported for each and every single item can help you determine that. Then we get the table of communalities. And then we have the initials extraction. This is a big difference between principal components analysis and factor analysis. In PCA, the initial is always 1.0 because it's only doing one extraction, in the sense that it's using the total variance for each variable to put on the main diagonal of the correlation matrix upon which the principal components analysis is going to be performed. But in factor analysis, common factor analysis, something else has to be used other than total variance. And what it's using in common factor analysis and maximum likelihood estimation is it's basically regressing each variable. So item 1 is regressed onto all remaining 19 variables, and it's basically giving an R-squared value. So 52% of the variance in item 1 is shared with the remaining